card. So example one here, this letter B is the true genuine alternating series. This one is positive, positive, negative, negative, positive, positive. This is not really alternating. Well, how would we determine if that guy is converging or diverging? Well, you wouldn't be allowed to use the alternating series test because you're only allowed to use the alternating series test on alternating series, not ones that are like positive, positive, negative, negative. There is another way to treat that thing with a theorem. So you use a theorem instead. And we are going to look at the theorem today, which I don't really consider one of your 10 tools. How about I'll consider it a half a tool? So well, I'm going to give you 10 and a half tools total. So this was my half. Mainly because you rarely use it, but when you will be using it once on this week's quiz 9. So you do need to learn it. All right. So when we use the alternating series test, which I'm going to go over in a minute, I'm going to abbreviate it A period, S period, T period, just because it takes so long to write out. I mean, if you look at alternating series test, it takes too long to write. So I'm going to call it the AST for short. Okay, let's talk about the classic alternating harmonic series, sigma 1 over n. You guys already know that this guy is divergent, right? That's definitely not alternating. Why do we know that it's divergent? Which test can we use on sigma 1 over n to show that it diverges? And I claim there's two possibilities, two
P
tests.
series.
P series.
Very good. That would be the quick and dirty way to show that 1 over n diverges. What's another way that's not as quick, but it'll still be doing the trick for you?
Integral.
Very good. Very good. So either of those two tests are appropriate to show that sigma 1 over n is divergent. Very nice. Okay, now what if we take the sigma 1 over n, but we make it alternating by sticking in this -1 to the n plus 1 factor? That will make it alternate. The question now is, will this series also be divergent? So we're going to take a look at, we're going to come back to this question later, but I want you to keep that in the back of your mind, that question, because we're going to answer it today for you. All right, is that guy divergent also? Yes or no? Let's keep going. So let's examine this thing called the alternating series test. Fine. First up, you got to know how to figure out if something's alternating. So if you take a regular series, sigma a sub n, and if that sigma a sub n has either a -1 to the nth in its formula or a -1 to the n plus 1 in its formula, and the b sub n part is always going to be something non-negative, then you have a true, genuine alternating series on your hands, okay? Now, there's many ways to deal with this alternating sign. So I need you to know these little weird exponent law tricks, because when we do power series next week, you're going to have to play around with this. So let's just do some fun and play with exponent laws. What if you had -1 raised to the n plus 2 power? Well, that can be rewritten. Really? Yeah, it can be rewritten as -1 to the nth times -1 to the squared. That's legal because it's equivalent. And the -1 squared is always equal to what? What happens when you take a negative and you square it?
1. And make a positive.
Yeah, that's just going to be +1. So you can just kill him off. And then who's left? -1 to the nth. And that's this guy here. That's what makes things alternate. Well, what if you had -1 to the n minus 1? That could be in a formula. Okay, well, if you use an exponent law on it and rewrite it as -1 to the n plus 1 times -1 to the -2, and just to remind you that when you take a product of like bases, it's the same as keeping the base but adding the exponents. So when you had -1 to the n plus 1 times -1 to the -2, that's the same as -1. And when I add these exponents together, what do I get? You see how these really are equivalent? That's the point. But then again, what happens when you raise a negative to an even power? This, if I rewrite this using positive exponents, it's the same as 1 over negative 1 to the positive 2, but we just got done saying negative 1 to the positive 2 is 1, so this is really just a 1. So negative 1 to the n minus 1 is exactly equivalent to negative 1 to the n plus 1, which is the other thing that you will see to determine that you really have a true, genuine alternating series on your hands. Okay? I just want to make sure that you know one when it hits you in the face. Like, oh, that's alternating. Okay, so the point is negative 1 to the n or negative 1 to the n plus 1 both have this pattern. They both go 1, negative 1, 1, negative 1, and that provides the alternating for your alternating series. Okay, now you're ready for the theorem. Here it is, people, the AST. So when you're performing the AST, you have to do two little mini proofs for me. You have to show two things are true. And if both things are true, then you can conclude convergence. This is, you guys remember, just to recall a little something back. Do you remember the nth term test for divergence?
Yeah.
Which Briggs likes to call what? What does Briggs or my math lab call it?
Divergence test.
Yeah, they call it just the divergence test, which is fine, but you know, I like to call it the nth term test. Do you remember that this test is a little bit limited and that you can only use it to conclude what? Convergence or divergence?
Divergence.
Yeah, you only use to conclude divergence. You're not allowed to say something converges with the nth term test. We already discussed this at length. But other tests you can, like, you know, the limit comparison test, which we went over on Friday and you just took a quiz on. That one, you can use it to conclude something converges or diverges, as the case may be. But the nth term test is limited because you were only allowed to say something diverged. Fine. Well, the AST, that's what I call this for short, you can only use it to conclude convergence. You're not allowed to use it to conclude divergence, okay? I'm just saying, so keep that in mind. All right, so you have to prove to me that the limit of a sub n is equal to 0 as n goes to infinity. And notice that they're not putting the negative 1 factor in there. They kill that off, and they just examine the limit of the positive portion of the formula to see if that goes to 0. If that's going to 0, that's a good thing. Then go on and prove that condition 2 is true, which means show that it truly is a decreasing sequence, that the terms are getting tinier and tinier as n goes to infinity. You're going to do this with either a mini proof, which I'll show you how to do, or you can prove to me that f prime of x is always negative. That shows me that f of x is a decreasing function, and this is a calculus 1 style of proof, okay? So there's a couple things to note about the test. Unlike the integral test or the comparison test, this tells us only if a series converges, not if a series diverges. Secondly, the second condition, you need those terms to be eventually decreasing. If they initially increase, but then after a while they are decreasing, that's good. You're fine. Okay, so now it's time. We're going to answer the question. Does this series, which is the alternating version of sigma 1 over n, which we know does diverge, does he converge or diverge? Okay, so we're going to do the AST, alternating series test. Okay, condition 1. Is it true that the limit of a sub n as n goes to infinity equals 0? And when you're doing this limit, don't take the limit with the negative 1 in it. Like, I don't even care about him. Just take the limit of the rest of the formula, which in this case is just 1 over n. Does this go to 0 or not? What do you guys think?
Yes, it goes
Yes,
to 0.
it does.
Good. So good news. Condition 1 is good. We're done. What about condition 2? Are the terms really decreasing? So you're going to do this the mini proof way because you can. So what do I need to show? I need to show that the n plus 1th term is less than the nth term. So I already know what the nth term looks like. It's 1 over n. But what's the n plus 1th term? Well, you guys know from your knowledge of n's and everything, you'll just replace n with n plus 1. Is this true or not? And I claim it is. So how do I show that? I'm going to do similar mini proof that we did when we were doing the direct comparison test. I compared denominators. Which denominator is obviously larger than the other one, the left or the right hand side?
Left.
Left.
Left. Okay, so you make your inequality. Then if I take the reciprocal of both sides, what do I do to the symbol?
Flip. Oh, I'll change it.
Yeah, and this is exactly what I needed to prove, that the n plus 1th term is always less than the nth term, which shows the terms are decreasing. Yay! So since both conditions are met, the alternating series converges. And I'm done with that example. So what's the overall takeaway from this? Because this is kind of exciting, I think. The takeaway is that sigma 1 over n diverges, but his brother, the one that alternates, converges. Let that sink in for a moment. Okay, so let's do another example. So example 3, here we have an alternating series. I know it's alternating because we got that -1 to the n plus 1 thing happening. And then we have n squared. Now, what do we know about his brother who doesn't alternate? Just sigma 1 over n squared. What about that series? You guys should know about him. Does he converge or diverge?
Converges.
Converges. Good. Why? What test did you use?
P series.
Series.
Very good. P series. So we know he converges. So what about the alternating version of him? Does that converge or diverge? Well, we're going to do the alternating series test. So condition 1 is the limit as n going to infinity. Does that really equal 0? Well, let's check it out. And again, don't consider the -1 factor when you're taking a limit. I don't want to see it. Does this limit go to 0?
Yes.
Yeah.
Yep. Okay, check. I just showed condition 1's true. Fantastic. Move on to condition 2. So now are the terms decreasing? And the way I'm going to show that the n plus 1th term is less than the nth term, that's just a fancy way of saying the terms are decreasing as they get larger, is I'm going to do the compare denominators trick. But what is the denominator? Like the denominator for the nth term is just n squared, but the denominator for the n plus 1th term is the quantity n plus 1 squared. So I need to show this is true. I have to show that's true. So I'm going to do a mini proof. And I think you see where this mini proof is going. I'm going to compare denominators of the n plus 1th term with the nth term. Now, who is obviously larger?
The left side.
Yeah, the left side. N plus 1, the quantity squared, has got to be bigger than n squared. And then if you take the reciprocal of both sides of the inequality, which means flip the symbol, aha, we just showed it's true. Therefore, we showed the terms are decreasing. Boom, the series converges. Okay, great. So it looks like everybody converges if they're alternating, right? No, don't even think that. Don't get too excited and think that every single alternating series converges. That'll be dangerous. Let's take a look at example 4, which is kind of hard because they didn't give us the formula. So the question is, do you know how to figure out the formula for this guy? Do you guys see a pattern here? If this will help, I'll give the first term a denominator. Then you may see a pattern. So the first term is 2 over 1. The next term is minus 3 over 2, 4.
N plus 1 over n.
Okay, say that again.
N plus 1 over n.
Good one. Okay. Now, if I start n at 1, I'm going to have a factor of -1 in there to make it alternate. So should the exponent on the -1 be n or n plus 1? Which one will make this positive, then negative, positive, then negative, as we're seeing here?
N plus 1.
Yeah, n plus 1 will work. Okay, so the formula for this alternating series is -1 to the n plus 1 times n plus 1 over n. Does everybody agree that that is a formula that will work? Do you see the pattern match?
Yes. Yes.
Okay, so, and that is alternating. So we're going to use the alternating series. Condition 1 is the limit as n goes to infinity of n plus 1 over n equal to 0. Well, when I use direct sub, I get infinity over infinity, which means I could go use L'Hopital's. Or I could use growth rates because I've got a polynomial over a polynomial and they're comparable growth rates because those polynomial degrees exactly match. So does anybody want to tell me what this limit is?
1.
1.
1.
Yeah, the lead coefficient over lead coefficient, which is 1. Is that equal to 0? No.
No.
So condition 1 is not met. What do? Well, don't bother going to condition 2 because you'll be wasting valuable time.
Diverge.
You're going to conclude that the series diverges, but not from the AST, not from the alternating series. Well, what do you mean? We're going to say it diverges because what is this test where you take the limit and test to see if it doesn't go to 0 and then you can conclude divergence?
Nth term.
Dirty test.
Yes, it actually diverges by the nth term test for divergence, not the alternating series test, because condition 1 is really the nth term test. And we're done with example 4. That alternating series diverges by the nth term test for divergence. Okay? Is everybody okay with this?
So that will be the case every time. Like if the first condition is not met, then it diverges by that. Okay.
You got it. It diverges by the nth term test if condition 1 is not met. You can immediately just say, boom, I'm done here. Nth term test diverges. Pretty good, huh? You should be happy that it's that easy. Okay. So now I'm going to do an example where, you're going to have to show me the terms are decreasing by using a derivative. So let's go over a little bit of Calc 1 review. Do you remember that when you had the graph of a function and they would ask you, hey, where is the function increasing and where is the function decreasing? Do you remember this from Calculus 1 at all?
Yes.
You guys are graduates of Calc 1, right? So hopefully you remember some of this conversation. We haven't done any of that in Calc 2. So let's just revisit the concept. You guys know that when a function is increasing, like right here, if I were to draw some tangent lines, the tangent lines all have positive slopes. And since derivative is really slope, that would mean that your derivatives would be positive right where your function is increasing. But what about when your function is going downhill? Like right here, it looks like my function is going downhill. Do you see that? And if I were to draw some tangent lines to those parts of the graph, the slopes are all negative. Yeah? So this is where the function's decreasing. And so these slopes, that would be your derivatives, would be all negative. Does everybody buy this? And we're done with the calculus review. So let's just recap. If your function is increasing, one way to prove it's increasing is you show it's increasing by showing that the derivatives are always positive on that interval, from here to here, say. But if you want to show your function is decreasing on some interval, fine. The way you can do that is, since the slopes are all going to be negative, the slopes of the tangent lines, just prove to me that the derivative is always negative on that interval, And boom, you've showed me the function is decreasing on that interval. So if you got this, then you're going to understand when I do condition 2 for this particular alternating series, I'm going to use this idea. Okay, so first up, condition 1 though. So condition 1, let's do that first because that's always, you know, very key. If that one fails, don't even bother doing condition 2. Is it true that when you take the limit as n goes to infinity, you will get 0? Now, when I use direct substitution, I get ln of infinity divided by infinity, but that's infinity over infinity. And I certainly could use L'Hopital's. That would totally be legit. Go for it. Or I can use growth rates. So who goes to infinity faster? The logarithm that's in the numerator or the polynomial in the denominator?
Polynomial.
Yeah, so he goes to infinity faster. So what does it mean the limit goes to if the denominator goes to infinity faster?
0.
Yeah, we'll go to 0. So boom, condition 1 is met. Fantastic. That means let's do condition 2. So condition 2 says, prove to me the terms decrease. Now, folks, which they say n plus 1th term is less than the nth term. Why am I not going to use the mini proof for this particular series since I used the mini proof for the other two guys before? And I'm going to tell you, it's the same reason why you wouldn't try to compare denominators using DCT. Because both the numerator and the denominator are variable. So it would be really too hard. You'd have to prove that ln n plus 1 over n plus 1 is less than ln n over n. And you've got too many things that are varying here. Both of the numerators and denominators are varying. So this would be too hard to prove using one of those cute little mini proofs. So don't even do it because of the variable numerator and denominator. See, before, at least the numerators were just ones. They were constant, and only the denominators are varying. So then we could use the cute little let's compare denominators trick. But here, you've got denominators getting larger as well as numerators, so you can't use the compare denominator trick. So what we'll do is we're going to take the corresponding function, ln x over x, and we're going to prove that f prime is always negative. That says prove right there. F prime is always negative after a certain x value, you know, at least past a certain point. Because showing that f prime is negative is showing that the function is decreasing. That's good enough for me. Okay. So anybody have an idea how to take f prime for this function ln x over x?
Quotient.
Quotient rule.
Yes, thank you. Quotient rule. Good job, guys. So you're going to go f prime, which is the derivative of ln x, that's 1 over x, times g, times the denominator, minus the derivative of the denominator, well, the derivative of x is just 1, times the numerator all over the denominator squared. So after reducing that first term, this is my derivative. Well, hell, is this always going to be a negative number? Well, let's just try a few values of x. So if you just make a table here, let's do this. Here's a little chart. So here I'm going to plug in some values of x, like 1, 2, 3, 4, 5, and then let's see what the derivative looks like. Now remember, I don't care what the derivative is, I just care if it's positive or negative. So if I plug in the number 1, the denominator for sure is going to be positive because 1 squared is positive. 1 minus ln of 1. What's ln of 1 equal to? It's a nice number. Anybody know?
0.
So let's have 1 over 1, but that's positive. Wait a minute, I thought you wanted us to show that f prime is negative. I'm gonna, but not yet. It will after a certain x value. Well, if we plug in x equals 2, of course the denominator is 2 squared, so the denominator is something positive. The numerator will be 1 minus ln of 2, but ln of 2 is something like 0.693 or something like that. So the numerator is going to be like 0.3, that's positive, and the denominator is positive. So this is going to be positive. Well, that's not showing me that f prime's negative. I know, but now watch. When you plug in a 3 into your derivative, you're going to get 1 minus ln of 3. And I claim that ln of 3 is something bigger than 1. I don't know exactly what it is.
1.09.
2.09, great.
1.09.
1.09, thank you. So when you subtract 1.09 from 1, you're going to get a negative numerator, and the denominator is something squared, so it's always positive. So you'll get a negative divided by a positive, but that's a negative number. And the same is going to happen when you plug in 4 and 5 and everything else. You're going to get 1 minus, for example, ln 4 over 4 squared. That's going to be a negative over a positive, which is going to be negative. So from then on out, as long as x is greater than or equal to 3, f prime is always going to be something negative, and that proves f is decreasing, which proves that my term a sub n is also decreasing. Boom! Condition 2 is met, and the series converges by the alternating series test, AST for short, and I'm done with this problem. So that took a little bit of work because you had to use some of your Calc 1 knowledge to do it. Okay? And yeah, I know it was a pain in the butt.
I have a question. So, like, what would you have to write for your proof to prove that?
All of this, everything I just wrote down.
All right.
F prime, starting with F prime, and then you would say, since F prime negative, the terms decrease, and the series converges by the alternating series test. So you would do it like that. Show me that f prime is negative, at least after a certain point, like we did here, x greater than or equal to 3 makes my derivative negative. And then f prime less than 0 means the terms are decreasing. And so condition 2 is met, and you're good to go. Does that make sense, folks? It is a proof, essentially, what you're doing here to prove condition 2 is being met. It's a mini proof, but a different kind of flavor of mini proof where you're using your calculus 1 skills. Pretty good, huh? I bet you didn't think your calculus 1 would come in handy sometimes, right? Is anybody excited, or is it just me? Does anybody care anymore? I don't know. All right, I'm going to make you guys do some work now, okay? You guys ready? I'm going to put you in breakout rooms, and I'm going to come visit your breakout rooms. So do you guys see this book right here? Did anybody buy this book? I'm going to check the chat. Go say yes in the chat if you bought this book.
Yes. Or I have it.
Yeah.
If you didn't, and if you're struggling in this class, I highly recommend you buy it. Okay? You should buy the hard copy. Okay, so in this book, I'm going to turn to section 10 point what? 10.6, alternating series, and I'm going to pick a homework problem out of here, and you're going to do it. Yeah, baby. Oh, let's pick something kind of fun. Oh, boy. Well, what do I got here? Yeah, that looks kind of fun. Let's do that. Okay, so I have one for you. I've got all cooked up. So let me key it up. This is not in your course reader, by the way, so you might want to write this down, because you and your buddy are going to be working on this one right now, okay? So here is an alternating series. Actually, I think I'll give you 2 of them to do. Ha, ha, ha! So I'll call this first one letter A. Sigma, k going from 0 to infinity, -1 to the k, all over 2k plus 1. So you try that one with your buddy, and then if you finish early, because you know what you're doing, let me give you another one for kicks and giggles. Oh my goodness, that one looks pretty nasty. Oh, what the heck, I like this one. Sigma k going from 2 to infinity, a negative 1 to the k, times the quantity 1 plus 1 over k. Yeah, I kind of like that one. Okay, so we've got 20 people in the room. I'm going to put you into 10 breakouts. When your breakout room opens, please go in there and work with your buddy, okay? See you later. What was
Professor-
A? Oh, sorry. There's A. Negative 1 to the k over 2k plus 1. And then B was negative 1 to the k, 1 plus 1 over k. You got all that, guys? Before you hit your breakout rooms? Okay, now I'll open all the rooms. Good luck. Summer. Guess I'll record now. Let that be a lesson to you. Don't miss class, because I don't always record everything, right? Okay, so here's the deal. If you are getting partial sums of an alternating series, you can use that partial sum as a good approximation of an actual sum and figure out even how far off you are. So here's the idea. The actual sum, the real sum of all infinity terms would be S, but there's no cute formula like there are for geometric series where you can figure out the infinite sum. So you don't have that at your disposal. But the infinite sum is a pretty close to your sequence of partial sums. You know, it's not exact. But what's the difference between your sequence of partial sums, Sn, and the real deal, the S? Well, take the difference, and then you'll get how far off you are. And this far off you are is called the remainder, and the alternating series remainder theorem says that remainder will always be less than or equal to the n plus 1th term, which is kind of cool. So watch closely in this next example. It's kind of fun. And if you're an engineer, you care about this, because engineers are always concerned with approximations and how far off you are with the real deal. So it turns out that this convergent alternating series actually adds up to ln2. Well, how did you know that? You just said that there is no secret formula unless you're doing a geometric. Well, once we get into power series, there's some cool series that you can figure out what they add up to, but I can't tell you everything now. We'll tell you then, okay? Just accept it, that this adds up to ln of 2. Okay, fine. Well, if you start writing out some of the terms, you know, 1 minus a half plus a third and so on, how many terms do you need to be within 0.00000, and that this should be a 1, not a 6? 0.00001, 10 to the negative 6. So what we want to figure out is how many terms do we need where it's pretty close to ln2 and we're within 10 to the negative 6 of it. So if you use this alternating series remainder theorem, and you now know how to get the n plus 1th term, because I just went over it in massive detail, how do you get the n plus 1th term for our guy, where the nth term is just 1 over n? What's the n plus 1th term? Come on, people.
1 over n
1
plus
over n plus 1.
Thank you. Oh, God, there is a God. Okay. So what we're saying is that we want this n plus 1th term, which we now know is 1 over n plus 1, to be less than 10 to the negative 6, because that's basically our remainder. And so the key here is to solve this for n. And that will, the n will give you the number of terms you need to be within that small distance, 10 to the negative 6 from ln of 2. Now, there's a few ways to solve inequality, to solve for n, but I'm going to show you my favorite way. I'm basically going to rewrite this as 1 over 10 to the positive 6, because that's what it's the same as. And then you guys know about taking reciprocals of both sides of an inequality. It's legit as long as you flip the symbol. So I just flip it from a less than to a greater than, and this still is true. But then this is just saying that n plus 1 is greater than 1 million. And then if I subtract 1 from both sides, I have a 1 million take away 1, which, you know, is 999,999. So if n is greater than or equal to 999,999, then we'll have enough terms to be very close to the actual sum ln2. Now that is a lot of terms, people. I mean, you have to add up a lot of terms, but that's why computers are so great. We could let a computer be in a loop and add up 999,999 of the terms of this series, you know, and compute that overall sum. Okay. So example 7, here's my example 7. They want us to, if we approximate the sum of this series by the first 6 terms, how bad would the error be? So, you know, the first 6 terms, there's 3 of the terms. Okay, fine. And if you added up all 6 of these terms, oh man, what would you get? You would get, you know, 1 minus a half plus 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. I use my calculator. I get 91 over 144. And so, you know, how bad of an approximation is that to the true infinite sum, even though I have no idea what the infinite sum is? Actually, I do, but I don't want to go there. Okay, I don't want to tell you. I think it's e to the negative 1. So the actual sum for this is e to the negative 1 power. Is that right? Yeah. But I digress. So I want to know how far off I am. So how far off I am is my remainder 6 is going to be less than or equal to the 7th term. But the 7th term is just 1 over 7 factorial. And 7 factorial is kind of a big number. It's 5,040, which is equal to point, I think this is approximately 0.0002. So the actual sum lies between 91 over 144 minus this error, and because it's plus or minus the error, 91 over 144 plus the error. So it's somewhere in between there, the actual. Okay, and that's all you need to know. They didn't ask us to find the n this time. Okay.
Wait, I have a question. Why did you get a to the 7th?
Because let's read the theorem again, shall we?
Is it because of n plus 1?
Yes,
right?
sir.
Oh, all right, I got
So
you.
if you read the theorem, it says that if you're trying to approximate the actual sum s by the sum of the first n terms, the remainder says you're going to be off by a sub n plus 1. So we were trying to approximate the sum with the first 6 terms. So we had to get a sub 6 plus 1, which is a sub 7, to tell us how far off we are from the actual. Does that help?
Yeah.
It's a cute theorem, and it's really good to help you just figure out how far off you are with the actual sum. And this only works for alternating series, though, unfortunately. Okay. All right, so now let's talk a little bit of quick note about some series. And folks, no one in the room has had me before for Calc 2 last semester, which is sad. No, wait a minute. I have a couple people. Just a minute. I lied. I think there's a couple people in there. You know who you are. I change my course reader every semester, so I hope you bought the new one. Because last semester I did not have what I'm about to tell you in there. So I tweaked it, and I tweak it all the time. So this is some really cool facts. And by the way, this will really help you understand series, and it'll help you understand power series, which we're going to start next week. And for those of you who plan on taking differential equations next semester, provided you pass this class, it'll really help you there because they do a little bit of series in that class. Not a whole lot, but a little bit. So I'm just warning you. Okay, when you have a series, any series, we all should know that this is a fact. You've got sigma a sub n, and if n starts at 1, then your first term is a1, and then plus a2, plus a3, plus a4, and so on and so on and so on. Fine. Who doesn't know that by now? That's scary if you don't. Now, what if you wanted to rewrite this series in a very special way, where you save the first term and you kind of pull it away, you kind of put it aside, but then you want to add all the other guys, because you're still representing all of the sum of a1 plus a2 plus a3 plus a4 and all those guys. So another way of saying it would be a1 plus the rest of the guys. Well, how would you do the rest of the guys? Well, you start at n equals 2 because, you know, the rest of the guys start at a2, at a3, a4. So this is another representation of the original series where you pull out the first term plus the rest of the guys. And this is true however many terms you want to strip away. They call this stripping out. So if you just strip out the first term, it looks like that. And this is a very good skill for you to have, of stripping out terms. Believe me, you have to do it in differential equations all the time. And when I teach differential equations, and I try to teach this idea of stripping, which isn't that hard, half the class goes, they've got all these tears and they're screaming. And I'm like, dudes, it's not that bad. I'm not doing anything tricky, I swear. So what if you wanted to strip out the first two terms and then the rest of the guys? Well, do it. You have the first guy, A1, plus the second guy, A2, plus the rest of the guys. But what do you say for the rest of the guys? Because the rest of the guys start at A3. So you just change your starting index to be 3. That's not hard. And then this represents the rest of the guys. Well, what if you want to strip out four terms? Okay, A1 plus A2 plus A3 plus A4 plus sigma, and then you just start your starting point at n equals 5, and that's still legit. So if you're going to do this for this series here, where we had 1 minus a half plus a third, you know, et cetera, and then we said, and I told you this, you had to accept it, that the infinite sum is ln2. What if I said, hey, I want you to start at n equals 2? By the way, this is not index shifting that we're doing, okay? Index shifting is a whole nother ball game. This is not that. So please don't get confused here. I'm doing something called stripping terms. So you could do an index shift, but we're not doing that. I want to just strip the first term out, so there he is, plus the rest of the terms. And then I just start my index at 2. Okay, and I stripped out the first guy. So this is supposed to be equivalent. 1 plus the rest of the terms had better equal ln2. So then here's the question, and yes, I'm going to ask you this on a future quiz or exam. Could be a true-false. What is this sum equal to, where you start at 2 to infinity? Well, I don't know how to do that. Well, yeah, you do, because I told you that if you start at 1, oh, sorry. Here we go. If you start at 1, it adds up to ln2. And if you strip out the first term, you get 1 plus this guy equals ln2. Well, check out this. All you have to do is solve this equation for the sigma 2 to infinity, negative 1 to the n plus 1 over n, because that's what they're asking for. So what would you do to both sides of this equation in order to solve for that sigma? Quick.
Factor 1.
Very good.
Minus 1.
Exactly. So your answer is going to be that sum is equal to ln2 minus 1, the first digit. Voila. Pretty cool, huh? So that's fun and play with series. So now what if I said, okay, well, sigma 1 to infinity, negative 1 to the n plus 1 over n, let's strip out the first two terms. So it's 1 minus a half plus the rest of the guys. So the rest of the guys, I would start at 3, go to infinity. And this had better equal ln2. So this has to be true. So then what if I said, what is this sum equal to?
ln 2 minus a half.
Yes. Yeah, you would solve this equation for that sigma, and this right here is a half, so you would simply subtract a half from both sides, so it'd be ln2 minus a half, and then you'd be done. Does this make sense? Because if it does, you're well on your way to understanding series and having fun and play with series. Okay, I'm going to finish and conclude right now. We're going to do a really, we'll do rearranging next time, but the hard thing we're going to do next time, well, I say hard, but a lot of students get it. It's not that bad. We're going to look at something called absolute and conditional convergence next time. We're still not done with the alternating series test section, because some of the meat and potatoes is yet to come. But I will do that for you on Wednesday, okay? Until then, I'm going to say ciao. Bye.